In practice 7, we're going to look at neural networks and how they're implemented in Python notebooks. So as in previous notebooks here, we'll start with section 0, and then we'll have a couple other sections, but you always have to run section 0 as your first attempt because it imports all these libraries that we are using. So as before, we are still using libraries like pandas and numpy. We're also doing some plotting, and we have sklearn, scikit-learn libraries as before. But we have this new library called Keras, and Keras is a well-known library for neural networks and deep learning, and we're implementing a number of features for that here. So those are set up. Now, Keras will use a library called TensorFlow by Google for the actual neural networks that we're using. Now you can use Keras for some different libraries, but in this class we'll use it with TensorFlow, which is a well-known neural network and deep learning library built by Google. We'll be looking at 3 data sets. Section 1 will be the iris flower data set. Section 2 will be breast cancer, and Section 3 will be the MINST, similar to the MINST data set. Again, this should be relatively similar. It's similar to what the data sets we've looked at before. So here's Section 1, again on the iris flowers. Section 2 is the breast cancer, and Section 3 is the Kaggle runs. And you can jump back and forth as long as you always run section 0 here, of course, beforehand. So, okay, let's go through this first one. If you remember, we'll bring in this data now. And the data is, we have 4 different measurements for each flower, and then the species is labeled. We're then going to set up the data. Again, in our data set, we're going to have 4 inputs and 3 outputs. There are 3 different kinds of flowers, so we're going to output 3 different possibilities. And again, there are 4 measurements for each flower as the input here. We're going to do some setup as before. We're going to read in an X and a Y for training purposes. We're also going to scale the data. This is particularly important in neural networks. They expect data to be either 0 to 1 range or -1 to +1 range. So we're going to use this min-max scaler for that. We're going to break the data up into some testing and training data here. And we're also going to do this categorical, what's called one-hot categorical output, one-hot encoding. So here's our 3 flowers, and we're going to, each one we're going to represent, we're going to have 3 outputs, and we're just going to turn 1 output on for each different flower. So in our first flower, we're going to set turn the first node on with a 1, and the other ones will be 0. And then the middle flower, the middle node will be on, and the last flower, the last node will be on. So again, this is real common in neural networks. It just says which of our output nodes, our 3 output nodes, will be on for each category. So we've read that in. We're often going to just display the shape of this data. It shows here that now we split up the data. We have 120 flowers in our training data. Each one has 4 features. And then we have 30 flowers in our test data, each with 4 features. Now for our results, again, we have 120 flowers, and there are 3 different possible categories, and same with the testing stuff. Now we're going to set up our network. This is what our initial network is going to look like. The code for it is right down here. We use what is called a sequential network. So each layer of the network will declare, and it is automatically connected to the layer before. The input layer is actually put in here. So we say we have an input layer, and the input size is declared up here as 4. So there's 4 inputs. And then we have a network. So here we create our network, and we give it some name. And now we're going to use that name, and we're going to add a layer. So that's our network, and then we're going to say add. And we're going to use these dense layers, 2 dense layers, actually 3 dense layers here. When we declare a dense layer, we specify the number of units in that dense layer and then activation that we're using. So you can see up above here is a kind of a picture of our network here. our input layer is 4 nodes. And then our first layer, which we often call the hidden layer, or the first in layer, has 8 nodes in this case, because we've specified down here that we're going to create a dense layer of 8. The dense means that every node in this network, like number 3 here, is connected to every one of the inputs. So 3 is connected to every one of these 4. So there's 4 connections going from the inputs to this one, and again that would be the same for each one of these. So that's what dense means, is every node in one layer is connected to every node in the previous layer. Similarly down here, we're using our iris network. We're adding a layer, and then we're going another layer that's called dense with 6. So this next layer is going to have 6 nodes or units, and we're going to call this, just hidden 2 is the name for this. I'm just calling it that. And again, this is a dense layer, so each node here is connected to every node here. So another way of thinking that is every node here sends its output to every node in the next layer. That's what dense layers go here. So node 1 here will actually get connections from every other node here, which they're just not shown for. I'm just showing all the connections into 3 and out from 3 here. Okay, so that's our second hidden layer. And then our final layer is our output layer. And that has the output size, which is 3. So we're going to do 3 categories here. And again, just as we kind of described up above here, with this, our first iris flower is going to be this node. So if this node goes on, it'll be the first iris flower. If this node goes on, it'll be the second, and this node the third. So for example, if we have one of these iris flowers, Iris virginica, I think that's what it is, here, and that's encoded 0, 1, 0. What we'd expect the output to be is that if we put in the measurements for those flowers, the output will be, this will be 0, this will be 1, and this will be 0. More likely this would maybe be very small, like 0.1. This would be very high, like 0.9, and this one would also be very low, like 0.1 or 0.2. And then the highest one here would be the most active node would be the flower. We are going to guess that it's that flower here. And again, we don't show all the connections. Each one of these nodes is connected to every one of these nodes. So we're just showing the connections going into 2, but there will be similar connections going into 1 and 3 from this layer. Okay, so that's our network setup. We do use a couple activations in here. This ReLU and softmax are kind of described up here. ReLU is rectified linear units. What that means is that any inputs that are below, that are negative, are zeroed out, and otherwise we just the outputs are just summed here. And then the softmax changes these. So if there are some values in here, they change these values to probabilities so that they sum to 1. So for example, if this is 0.1, maybe this is 0.8, and this is 0.1, so the sum of all these would be 1, the probability. So that means we're 80% sure this is the unit, we're 10% sure this might be, or 10% this might be. So it's just kind of one way to think of it, but the softmax would make these units output sum to 1 and be similar to probabilities. So that sets up our network here. Now we have to compile this network. We compile this. We have to specify some things like our optimizer and our loss function, and we're not going to go into too many details here. There's different optimizers, but we're using one common one called Atom. For categorical data like this, where we have the data split up like in this sort of structure here, where there's one category, each element or input is tied to one category. We use this cross-category empathy method of calculating loss, and again, that's not that important. And accuracy is what we're going to use to measure how well we do. And that'll just show us our prediction accuracy. And this is similar to what we've done before. So often we'll just set up our networks this way in this class and not worry too much about the other options. And now we actually do our training. This is called the fit function. We use our neural network and call the fit function. And we specify our input, our training input and output, and we also have our testing input and output. And we're going to run this. What this will do is run through, again, we have 120 samples in our input and 30 samples in our validation or test site. So it'll run through all of these. Let's just see if we can run this. Let me go back up here. Let's see. I've done that, done this. Now when I run this, I should see this run. And I'll start calculate this, and it should calculate these relatively fast with this simple network. Later on, this will be much slower as we go. But it'll calculate each one of these. It'll run through all 120 flowers and test it out and tell us what our accuracy is. Here's our accuracy. It starts at only 35%. And then our validation accuracy, this is the accuracy with the testing set, and it's only 26% here, so very poor. And then it trains it over time here. So we're going to do, we specify the epochs is how many times we run through all the flowers. So after 11 epochs, we're up to 61% here, and our testing accuracy, our validation accuracy is actually 66. That's really good. It keeps going. Again, we get kind of stuck at a spot for a while and eventually start climbing up again, getting all the way up to 70% for basically both accuracies. This is the training accuracy and this is the testing or validation accuracy. There's also something called the loss here, and we'll talk about those in just a sec. So after we've run the training here, we will print off the final value. So the final accuracy value is 70%. This is actually not needed, but this is just, if we're doing this printout, this is just recalculating this final validation accuracy here. We can plot this training data here. Generally, you'll see the accuracy start low and go upwards, and again it might go up and up and up, and we like this to go up to about 100%. Now we're at about 70% here, which is good, but not optimal here. So we should see this accuracy increasing over time. The loss function also should go down here. It will start high and go downwards as we go, and we'll see the loss function go down. And as the loss function gets towards 0, that means your training is kind of no longer effective. So you, but right now it's still going down. So we should probably be running this for even more epochs because this loss function is still pretty high. When it gets down to like 0.1 or 0, then more epochs is not going to help our training. So your job is to improve this network. Go up here, see if you can change, maybe run this for more epochs. You could also consider changing the number of neurons here. We have 8. Right now we have 8 in our hidden units. This is kind of how many internal features the network can keep a track of here, and so it's sometimes helpful to have more features. So maybe we'll want this one to be 20 nodes. And again, you can also change the other network size too. Whenever you make these changes, go back up to this where you're setting up the neural network and run these lines of code again all the way down. Run all this, and then you can do the training again, and then you can print off your results and see how you're doing. So here we're seeing again the training loss going down further for us. So if you get the network set up correctly, you should get very high values. I'm able to, like in this example, get up to 96% accuracy for both the training data and the testing data. here's my graph. It went up pretty well, and then I had a lull, and it went back up. And again, my loss function is down here. So again, it's very low. So I'm running this for 200 epochs. So that's kind of suggesting that running it for more epochs is probably not going to help at this point because the loss is so low. The loss is used for calculating how much to change the weights. And so when the loss gets down low, yeah, the weights will not change. And we'll look at options for that in a future lessons. So it's your job, improve this network, try some different values, and again, each time, remember, go back up to task 1 and recreate the network and do things. Next thing is then once we have the network trained, we can make a prediction. We did this before in another thing, but here's one sample measurement of a flower, and we can create a list with those measurements in place. We can then, because we transformed or scaled the original training data, we have to transform this data, and then we can make a prediction for that. Now this prediction is just going to print out some things. So in this case, let me just run this again. These are values, and again, these are stored in scientific notation. So the -1 means that we shift the percent over. So we are 0.99% sure it's this. This is -3, so we'd shift this over 3 places, and so that's much worse value here. And maybe let's see if I can change that actually. So here is our predictions here, and again, it's hard to read this format, and I have trouble formatting it clearly here. So this is what it is really. So this is, you can watch the negative here. This says move the decimal place over 1 spot here. So this is 0.9. This one moves over 3 spots. So that's 3.005, and this one moves it over 6 places here. So we are fairly confident that it's this first flower, 99.4%, and it's very unlikely it's either of the 2 flowers. So we find the maximum of those arguments and we print off the species, and this is the species we think it is. And so you can go through here and try putting in this information and see what it predicts for that type of flower also. Okay, next we're going to look at the breast cancer data, and again, we've looked at this before. If you're just jumping to this point, make sure you run section 0 before this. So we're bringing in the information. So remember, we have malignant or benign tumors as our 2 diagnoses, and then we have all these features. We have 30 features that we're going to use to categorize these tumors, and again, some of them are rather large and some of them are rather small. So we're going to set up our network. We're going to have 30 inputs and 2 outputs. The 2 outputs are going to be either malignant or benign. So one of the cells is going to be malignant outputs, and one of the outputs is going to be benign here. So that's how we have that set up. So read in the data, grab the inputs, grab the outputs here. Now the outputs are in our words here, M and B's. We're going to reset those with a label encoder, and so that'll change this to a number 0 or 1 for that. We're going to scale the data again. We're going to split the data into training and test data, and then we're going to use this one-shot encoding for the outputs, both the training and the test outputs here. So here's our data. We have 455 tumors we're going to use for training, and each one has 30 features. And again, we're going to have 450 tumors we're using for the outputs, and each one has 2 possibilities, benign or malignant. And for testing, we've broken off 114 of the tumors they look at for testing purposes. We're going to set up our network. There'll be 30 inputs layers here, and we're just going to start with 32 hidden units in the first network, and no, actually we're gonna change that. So I'm going to change that to 10 hidden units in the first layer and 5. So that's what I have here, 10 and 5. So my input is set in the size is set up here to 30. We then have 10 units in the first hidden unit layer, and then 5 units in the second dense layer, and then this is our output, and our output size is 2. So we're going to set up our network this way and get that running. As you get to more complicated networks and larger ones, it'll take longer to train. So initially when I start these networks out, I like to keep them relatively simple. So we set up our network, we then compile the network, and again, we're using these same sort of features which we'll use in a lot of these cases. Categorical cross entropy lets us do these categorical or classification problems, and we're going to look at accuracy as our output. Then we're going to train the network, and again, this might take a little while. Let me see what this error is. So you have to make sure my inputs match up here, and something's not quite right. I'd forgotten to run these. I'd looked at these cells above, but I forgot to actually run them. So I was using my iris data here instead of my cancer data, so it was getting confused. So now I should be able to train this network, and it should run through here. Okay, so now it's doing our calculations. So again, the initial accuracy is only 38%, and the validation or testing accuracy is only 33%, but it improves over time as we go. And again, we're doing this for 50 epochs here, running this through. And at the end, after 50 epochs, I have to keep scrolling down. There, at 50 epochs, I get up to 92% in the training accuracy and 93% validation. And this is actually quite rare for your validation accuracy to be higher than your testing accuracy. So it is generalizing. So that means it's predicting as well for cancer tumors that it has never seen before, never trained on. It is doing as well or better than for the tumors that it has trained on and worked with. So now you should want to compare this. So we are at like 93% accuracy. Now this is about what we were getting. I kind of averaged some students' examples. We did this in project 2. We did k nearest neighbors, support vector machines, and decision trees, and these are some sample numbers from there. So you have to compare your initial run with these 10 and 5 hidden layers and 50 F-box up here, how that compares to this. Try changing the hidden units and stuff, and again, when you make those changes, make sure you make the changes. You can change the network structure here and here, and you should redo this this network, recreate the network, recompile the network, and then retrain the network. And here you can specify the epochs here. So and then you can see how your accuracy is doing here. And then you can also, it's sometimes useful to plot this accuracy here, so you can see how the accuracy went up and down. And again, the training loss, again, now the training loss is still pretty high, 0.2, so maybe running for additional epochs would be helpful in this case because it hasn't become 0 yet. So okay, so work with the cancer data here, and again, get some, where's the task? Yeah, answer these 3 questions related to the cancer data. The last thing we're going to look at is a Kaggle challenge here for digit recognition. Now, we've looked at the MINST data set before. This is a different version of this, and this comes from Kaggle.com. Kaggle.com is a well-known machine learning site that hosts a lot of fun competitions, some of them actually for prize money. We're going to do their digit recognition challenge here. Okay, I forgot to link this in. So we'll go do this digit recognition challenge here. So the first thing you want to do is go to Kaggle and register. When you go to Kaggle and register, your profile will be up here. You can also click up here and get a link to your account. So once you have that link, paste that link in here so I also can see where your account is and that you've created it. Next, go and or join the digit recognition challenge. You can follow either of these links. So here, I think this button will say join initially. I've already joined, so now it says submit predictions, which we'll do in a little bit here. And again, this talks about the challenge here. It also has all the data that we'll be using for the challenge and talks about that. There are actually sample kernels where people have submitted things. I'm going to and there's some really good advice on how to make really good kernels here. And there's a whole discussion board and a leaderboard that shows how people are doing. So this is all part of this. But I'm going to go back to overview because that's where we're going to do our submit later on. Okay, so you've registered for Kaggle and you've joined the digit recognition challenge. This is just a kind of a learning challenge on Kaggle that's set up. So this is like our other MINTS database, but it's actually a lot larger. We have 42,000 images, each 28 by 28. So the old ones were 16 by 16 pixels. These are larger, 42,000. And then they also give you some hidden or submission data, 28,000 images, and these are the same size, but these are not labeled and you're never told what these are. And so your job is to make predictions on these 28,000 images, submit those, and they will score those. So they never tell you what the actual digits are in these images. So the first thing, we're going to download this data here. Now this will take a couple seconds. This is a huge, or not a huge, a larger data set. We'll get into much larger ones later in the course. But it does take a while. You see this running for a while. Now I've already downloaded this from Kaggle and put it up in GitHub because in GitHub I can download this directly into this area. If you are working on your own machine, you can actually download the data directly here as a zip file and save it on your machine. You can just download all the data. If you're working like with a Jupyter notebook, sometimes that's helpful. Okay, now we have the data downloaded. It shows us 42,000 28 by 28 images, 28,000 in our submissions. Here's our sample image here. Again, here's the label, what kind of digits. So this is a digit 4, and here's all the pixels here. It's hard to see that, so here's another view. That first value is a 4, and here's again, most of the pixels are zeros, are black, but there are some white and gray pixels here. So here's each of the sample values here. So we're going to do some setup with the data. As before, we're going to what we had to do is do some reformatting of the data so that we could view it as an image here. So we reshaped it as a image, and now we're reshaping it back as just a list here. So there's some reshaping involved here just so we can view it or not. So that's what this part is. We're also going to scale it. Here we know all the pixels are grayscale pixels that are each value is between 0 and 255 for grayscale. We want the values between 0 and 1, so we're just going to take every pixel and divide it by 255 to scale it. So we can actually do our own scaling here. We don't have to use one of the built-in scalers. We're going to take the training data and split it up into some training and some testing data. Now we have separate submission data, but again, we can't really use that to evaluate our model because we're not told what the answers of that are. And again, we're going to use this categorical one-hot encoding. So like a number three, every output will be represented by 10 numbers or 10 units. And number 3 would have the third unit on as 100%, and everyone else would be off for that. Okay, so then we can print off this data again. Just so of all the data, again, we started off with 42,000 images in our training data, and we're breaking that up. 90% of it we're using here, and 2% we're using, 10% we're using for testing purposes. We want to use as much as we can for training. The more training data we have, the better. So that's why I'm doing a 90-10% split for up here. In other ones we've done an 80-20% split, but here I'm just doing the test data is only 10% of the rest of the data, but it still gives us 4,200 test digits, so that's a lot. Okay, our network, we have our input is 784 pixels, 28 by 28, and we multiply that out, we get 784 inputs. Right now I'm only using 10 layer units in my first hidden unit, and 20 and then 10 as my two hidden units. And the output's always going to be, again, 10 units, because again, we're going to encode the digits 0 through 9 here. So this is all we have it set up: sequential network, a dense layer with 20, another dense layer is 10, and then our final output layer with our output size. So this is our input size, and this is our output size all set up. So let's set up that network. Again, we're compiling this network the same as before. We're going to train the network here. And now this might take a little while longer, especially when you make larger networks or train them for not. Right now I'm only doing 10 epochs because again this takes a little while. So if you make a more complicated network and do this for 200 epochs, you might have to just sit and let this run for half an hour or so. Later on, we'll at times run this overnight sometimes. So okay, so here's my accuracy, and again, I started with an accuracy of 83% and got up to 96%, and then for the testing, the validation stuff, I was at 91% and got up to 95%. I can predict my final result is about 95%, and I can plot my results here, and again my accuracy went up here, and my loss went down, but again it's still not zero. And one thing we'll talk about is that we'll talk about ways of improving this later on. Right now, if my loss is not actually going down anymore, it probably means my learning rate is too high, so we'll talk about that in a future week. Okay, so once we have that, we can create a submission in Kaggle or for Kaggle. So this creates, remember we have all these submission images. We have, let's see, how many did we have? 20-some thousand submission images. 28,000 images which are not labeled. We don't know what they are, so we have to predict those. So this code goes through all 28,000 images, predicts what they should be, and creates a file, and I am calling it this. You can, of course, change that name, but right now it's just called CIS3115 submission.csv file. So this is what is called a comma separated value file. It just stores it as a text file here. And we're going to submit this to Kaggle. So your first job is just to submit this to Kaggle. Now, if you're on a Jupyter Notebook, it'll just save this submission file in the same folder as your Jupyter Notebook on your PC. But if you're using Colab like I am right now, it's storing it in the Google Cloud here for Colab. So I have to go up here to this arrow here, click on this, go to the Files tab, and I just select the left arrow, click on this Files tab, hit the refresh button here, and then I should see my file here. I'm going to right click on it and choose download, and download it to my file, to my downloads folder or someplace like that. So it's going to say store it there. And then now I can go into Kaggle. I can choose, again, I'm in the digit recognizer location, and I'm under the data or the overview. I can submit a prediction. It says upload a file here. I'm going to go look in my downloads and grab it. Since there was two of them, it actually put one after the second one, so that's why I'm selecting the second one here. Open that up. It's read in the file. I can give it a brief description, recorded version, and then I can make that submission. It will score my results. It'll actually see how I'm doing and give me a response. So I scored 94.9%, which put me ranked as 2,185th of all the people who've tried out this challenge. So hopefully in the future we'll learn to move up some from this, but that this is the current one I submitted for this. Okay, so your task 6 is to submit just this version here, and then task 7 is to try some improvements. Try to change the number of hidden units or more epochs or both, and see if you can get a slightly better score and submit that. Make sure you record your initial score and any other scores you submit to Kaggle here. And just a note, in future weeks we'll be studying methods to improve your scores, so don't be disappointed if you are ranked around 2,000 here. Maybe you can get up to 1,000s before next week, but in future weeks we'll learn some more methods to improve your scores here. So hope you enjoy this.